Okay, let's get started. The intention of this short video is simply to give a few examples to help explain the concept of effective nuclear charge. So we're going to take three atoms, all in the same row, all in the same period, sodium, magnesium, and aluminium. So we've got sodium, magnesium, and aluminium. Oops, aluminium, not aluminum. And we are going to write the atomic number for each of these, Z. So that is going to be 11 for sodium, 12 for magnesium, and 13 for aluminium. This means that the electronic configuration for sodium will be 1s2, 2s2, 2p6, 3s1. And magnesium will be 1s2, 2s2, 2p6, 3s2. And then finally, aluminium is going to be 1s2, 2s2, 2p6, 3s2, 3p1. Perfect. Okay, so there are three things that we need to think about when we are trying to understand effective nuclear charge. The first of which is going to be the nuclear charge itself. So let's look at this. The nuclear charge of sodium, that's going to be 11. The nuclear charge of magnesium, well, that's 12. And the nuclear charge of aluminium, well, that's 13. Simply the number of protons that there are in the nucleus. The next thing we need to think about are the valence electrons in each of these atoms. So with sodium, going to look at level 3, there's one valence electron. Then with magnesium, we can see that there are those two 3s valence electrons. And then finally with aluminium, we can see that there are the 3p and the 3s2 valence electrons. So sodium has one valence electron, magnesium 2, aluminium 3. Finally, we need to think about the shielding electrons that are present. Sodium, 1s2, 2s2, 2p6, 10 shielding electrons. Magnesium, 1s2, 2s2, 2p6, 10 shielding electrons. And aluminium, 1s2, 2s2, 2p6, again, 10 shielding electrons. Okay, let's give a pictorial representation of what we've just been talking about. So let's have sodium, 11, and then we can draw this. This is the positive nucleus, and we're going to surround that with our 10 shielding electrons, and then we're also going to include our one valence electron. Draw that around there like that. Dun, 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 dun. And we can see it's that valence electron which is going to be pulled towards the positive nucleus. Now let's draw exactly the same for magnesium, but now of course we have 12 protons in the nucleus. So there's our nuclear charge 12. We're going to now draw the shielding electrons, which remember are still 10 shielding electrons. Draw those around there. And then we're going to put in our valence electrons, of which there are 2. Excuse me. There we go. It's our valence shell, 1, 2 electrons. And of course, those are being attracted towards the positive nucleus. And now we draw the same for aluminium, 13 protons in the nucleus, so the nuclear charge is 13. There we go. Boom, boom. Now we'll draw the 10 shielding electrons again. There we go. They go around there. And then we're going to draw those 3 valence electrons, like so. 1, 2, 3. and of course each of those are going to be pulled towards that positive nucleus. Now hopefully when you look at this picture you can see that the nuclear charge increases from sodium to magnesium to aluminium, but you can also see that the shielding electrons remains constant, 10 for sodium, 10 for magnesium, 10 for aluminium. That means effectively that the amount that the positive nucleus can pull on any valence electrons increases as we go from sodium to magnesium to aluminium. As a consequence of the amount with which the nuclear charge or the positive nucleus can pull on the valence electrons, as a result of it increasing from sodium to magnesium to aluminium, things like the atomic radius will decrease. So for magnesium, in comparison to sodium, the nucleus can pull more on those valence electrons, and as a consequence, that atom will be smaller than a sodium atom. And even more so with aluminium, it will be smaller still than the magnesium and the sodium. We can also use the idea of effective nuclear charge to help us understand electronegativity, the amount that the atom can pull on electrons in neighboring atoms. We can see that the ability of the sodium atom to pull on electrons is going to be smaller than the amount that magnesium can pull on those outer electrons or neighboring electrons in the case of electronegativity, and that we can see that aluminium will be able to pull even more. We can also continue and use this idea of effective nuclear charge to help us understand things such as ionization energies. We can see here that with respect to sodium, that outer electron, that valence electron, is not being pulled. The amount with which it's being pulled by the positive nucleus in relation to magnesium and aluminium is less, and as a consequence of being pulled less, that valence electron in the sodium atom can be ionized, can be removed more easily than magnesium and aluminium. So, in essence, having a good appreciation of the concept of effective nuclear charge helps you describe and explain trends in the periodic table, i.e. trends across rows in the periodic table, such as atomic radius, such as electronegativity, such as first ionization energies, and electron affinities. I hope that this short video has helped explain effective nuclear charge.